So given that A is diagonalizable, we want to show that this similar matrix, u to the negative 1 AU, is also diagonalizable for any invertible u. There are some assumptions being made here that, of course, A is n by n in order to be diagonalizable. And then for this product to make any sense, u also has to be n by n. But without that, we really wouldn't be able to proceed any further. So yeah, if A is diagonalizable, then basically what we're going to do is start by the math statement of what that means. So I will turn that into math. So there is some invertible P so that P to the negative 1 AP is D, where D is diagonal. And so our goal here is pretty much going to be to show that this thing is diagonalizable, which means that we want some Q. I won't use the same letter, so some Q, so that Q to the negative 1 times this thing is, and I'm not going to use D, maybe I'll call it D prime, where D prime is diagonal. And so how we're going to construct this, or how we're going to determine what this Q is going to be determined from the information that we're provided here. P to the negative 1 AP is equal to D. And I can basically just find a way to sort of blend these two things together. And I can do that by pretty much just saying that these two things should be P. And hopefully this works out because the structure is really the same and those two things are the place where P is. So let's see what happens if we do that. So I'm going to choose Q. So that UQ equals P. And so in other words, I can solve for that because I know that U is invertible. That means that Q equals U to the negative 1P. And then if I want to find the inverse of this, that means that Q to the negative 1, and we're going to have to go back and recall some inverse properties, but if we apply that, it's going to just reverse the order, if you remember. So that's P to the negative 1 times U. And so now I'm going to investigate what happens with my U to the negative 1 AU times Q. And if I plug all this in, I'm going to get P to the negative 1 U times U to the negative 1 AU, and then times my Q, so U to the negative 1P. And the way I chose this intentionally so that these things just turn into P, and that's what we can see happening here. These guys are just going to be the identity, and these guys are just going to be the identity. And so when we simplify this, I actually just get P to the negative 1 AP, and that's what I was hoping for because I know that this is my diagonal D. And therefore, there is such a Q, and in fact, this whole thing is diagonalizable. So U to the negative 1 AU has some Q. I can, again, always make sure I state invertible, but it's going to show up in the next line. So that Q to the negative 1 times our matrix times Q is diagonal. So U to the negative 1 AU is diagonalizable. And that's the proof.